Sensitivity analysis is also called what-if analysis. Typically, you fix all but one parameter to test how your solution to linear programming is affected by changing that one parameter. Let's recall that the max and the multi-max example we used before. Two computers have different profit margin. Both require testing and assembly. We know their corresponding usage and capacity. We need to use linear programming to figure out how to produce based on the available capacity to get the highest profit. We find that the best production plan will use up both the testing and the assembly resources, so it can be solved through the two resources constraints equations. Once the optimal production plan known, then plug it back into the objective function, we can calculate the best possible profit. However, usually the solution won't satisfy the manager. The solution only won't satisfy the manager, since the solution is just based on the specific problem parameters. What happens if some parameter values are estimated wrong or changed in the future? We need to get prepared for that. For instance, how should we adjust the production plan if a margin is changed? Or we may be interested to see under what conditions one of the products will stop producing. Okay, all of these relevant questions can be addressed through sensitivity analysis. As we mentioned before, sensitivity analysis is basically the what-if analysis. We change one parameter while keeping all the other intact to see how the solution will be altered. For linear programming, sensitivity analysis targets on two perspectives: objective function and constraints. For objective function, we can test the coefficient of variables. Then for constraints, we can work on three different things, such as coefficient in the left-hand side function, the constraint constants in the right-hand side, and adding one more new constraint. In today's discussion, I will show you how to do the sensitivity analysis on three issues, which are highlighted on these slides. So they are So first, I will check objective functions coefficients. Second, I will work on constraint constants. And the last one, I will work on the new constraint. Okay, now let's start with the sensitivity analysis with respect to objective function. We adjust the coefficient to a certain variable while keeping everything else unchanged, and check what will be different in our final optimal solution. In our original setting, the profitability of multi-max is $800, much higher than that of max. Now suppose our further marketing study finds that multi-max can only be sold at a price of $400, not a penny more than the price of max. What does our objective function should look like now? Okay, remember, x1 is for quantity of max and x2 is for quantity of multi-max. So then in our current setting, both computers sell at $400. So this is our the new objective function. Now let's do the sensitivity analysis. First, start with the 800 profit margin for x2, the multi-max. This is the graph showing how the ISO profit line at the optimal solution looks like when the profit margin for multi-max is $800. on this line, all the points on this red line will generate the profit of $742 and $800. Okay, now, what's the new profit margin for Multimax? $400 instead of $800. So if we still want to get the same level of profit as before, how does the corresponding ISO profit line should look like? Let's try to figure out first its two intercepts. To get this target profit, $742 and $800. Okay, let's suppose we get it by produce only max. We know that is to determine x1 and by assuming x2 equal to 0. So then we can calculate that by divide that $742 and $800 divided by $400. Then we can get its resulted quantity. That give us the intercept, which is exactly on this red line. We're using these pink dots to represent it. Okay, now similarly, we can get the other intercept. So the other intercept should mean to produce, okay, everything, produce only the Multimax to get this target profit. Since the Multimax profit margin is halved, so you can expect the quantity is doubled. So this is the intercept. Clearly, it is above the red line. Now we can draw the updated ISO profit line in pink. It shows that when Multimax is less profitable, the ISO profit line is steeper. This is because we put x2 as the vertical axis. A lower margin means a higher intercept. Okay, now what if we increase Multimax margin? How does the ISO profit line look like? It becomes steeper or flatter? It becomes flatter. So if the margin is just increase a little, then the ISO profit line will turn a little bit flat. So you can see corner B is still the optimal solution. But what if the margin is increased a lot? Then the ISO profit line will turn very hard. So corner B is no longer optimal. The new optimal solution is at corner A, corner point A. So as you can see, this corner point A is no longer on the blue testing constant line. So that means testing is no longer a binding resource. Now, here we can summarize the impact of the margin changing. It will change the slope of objective function. The optimal solution may or may not change, depends on how deep the margin is changed. But the optimal solution is still on one of the corner points. The binding resource may or may not change, depending on whether the optimal solution is changed. Okay, the reason to get this observation is that the unit margin is the coefficient in the objective function.